That seems reasonable. It's like the orange school. Oh. There's like 2,000 strands. This is 400 in there. In every year. There's like 20 academic that's perfectly using the community plus that. One per year. So you're telling me that there's kind of like 80 people. Oh, this I don't know. I don't know. Digital and any questions?
We're gonna go over the quiz from actually. No, never mind.
I suppose we can. There's no reason like we cannot.
Just confused on the last question.
Okay. Oh, that's a pretty good one. Okay, so let me point that out.
Oh, I meant the homework exhibit, the homework.
Oh, the homework. Oh, okay, yeah. Oh, sure, we can do that here. Still got about 40 seconds. I used to display a binary clock. Binary clock. So the binary clock is not really truly binary because it just has a binary number for the hour, a binary number for the minute, and a binary number for the seconds. But there are still 60 seconds in a minute and 60 minutes an hour, and 24 hours in a day. So it's not truly binary. It's more like binary coded, regular clock.
Right.
Otherwise, you want to have a power of 2 of seconds in a day. That would be.
Also probably be a little annoying.
Yes. All right, it is good time, so I'm gonna get started here. I will start with a announcement that I made just today, okay? And I wrote this module today because I just felt that, I could do this, and I think it's not a bad illustration of recursive definitions. So it is not mandatory reading. If you already know how to read the section notation, there's no need to read this part here. But this is my attempt of explaining the segment notation or summation, but using a recursive definition. So if I were to skip all the way, this is the definition. So the definition goes like the sigma, or if we want to sum where I start with B ending with E. And then each term we are adding is f of I, basically it's just a function applicable to the index. Then it is based on the ternary expression. If B is less than E, oh, I got it wrong, it is the other way. If B is greater than E, then you return a 0. Otherwise, you return the first f applied to the first number, and then plus the sigma notation of the rest. So it is a recursive definition to do basically the same thing. And let me go fix the error, because I can't stand it when I publish something that is incorrect. And this is also how you get to see how I author this content. Oh, okay. Let's get this one over here. All right. Give me a second here to fix that one, because I can't stand it when I got the logic wrong. All right, so it's right here when E is greater than E, because the beginning index is supposed to be less than or equal to the end index. And I got it all wrong. In the other example, get all this fixed. Run my trusty scripts, get everything updated on the server, and then come back here and refresh, and they should all be updated. All right, so let's take a look again. All right, so there we go. So this one is correct. So I'm turning the sigma notation into a recursive definition of the sigma notation. You're not required to read this part. In other words, I will not be asking specific questions about this particular module. And then I also use define the other big operators. So the other big operators are, I think I'm missing some portions of my original document. I don't know why. So the other big operators is pi, which is the product, and then we have the big or notation, and there's a big and notation, but I'm not sure why the rest is missing. Let me double check. I do something stupid. Probably because this thing here is incorrect. So we can left, click wedge. Right. Okay, well, somehow the notation doesn't translate, so I have to kind of fix it. And then I explained, is this really necessary? In other words, for something as simple as the summation notation, is it really necessary to use a recursive definition? And I'll fix this so that you can read about it. All right, so there was that. All right, so now I got a request to talk about the assignment that is due this morning. So we'll go ahead and talk about that. And that has to do with relations. There we go. Yeah, relations homework. And I'll just go ahead and do a quick review. So do you want me to just talk about the last one or the whole thing?
Just the last one.
Just the last one? Sorry?
Would you actually be able to go?
I can go over the whole thing, sure. Yeah. Okay, question number 1. Consider the not equal to relation over all integers. Which of the following relation properties apply? It is not transitive because 1 does not equal to 2, 2 does not equal to 1, but 1 does equal to 1. So it's not transitive. It is symmetric, yes, because 1 does not equal to 2 and 2 does not equal to 1. It is not totally ordering because it is not transitive. It is not reflexive because a number is not equal to itself. Okay, so it's not reflexive. It is not partially ordering because reflexive is false, and it is not anti-symmetric because 1 does not equal to 2 and 2 does not equal to 1, and yet 1 equals to 1 in that case. So it is anti-symmetric. Maybe think about it one more time. Oh, it is not anti-symmetric because 1 does not equal to 2. Confused. Question number 2, now we consider equal to. Equal to is definitely symmetric because 1 equals to 1, 2 equals to 2. So since the two things on the two sides of the relation are exactly the same, it is automatically symmetric as well as reflexive. It is also anti-symmetric. There's no way we can find x equals to y when x and y are different. So it is automatically anti-symmetric. And as a result, it is partially ordered because we have symmetry, we have anti-symmetry, and we also have transitive. Because equal to, it has to be transitive. If A equals to B and B equals to C, then A equals to C. Because A, B, and C, they all have to be the same under this relationship. And it is not totally ordered because 1 and 3, for instance, are not related in any way because they do not equal to each other. Yep.
Is there partial credit for this, for any of this?
Yes, and that's why most people do not get an integer value for the score. It depends on how many of the correct one you got. So that's partial credit. Number 3, if R and S are both relations defined over X, and we also know that R intersecting with S is reflexive, then what do we know for sure about R? Well, it is reflexive. That's the only thing. There's nothing else. Question? Okay. Number 4, consider the less than relation over integers. 1 is less than 2, 2 is less than 3, and so on. It is anti-symmetric because there's no way to make the conjunction true on the left-hand side of the implication. If you're thinking, I have no idea what you're talking about, that means you are not familiar with the anti-symmetric quality or property yet. It may be a good idea to get more familiarized with the definition. But the key is there's no way I can find A is less than B and B is less than A. That just doesn't happen. So if the conjunction is guaranteed to be false on the left-hand side of the implication, then the implication is guaranteed to be true. So it is definitely anti-symmetric. It is not reflexive because a number is not less than itself, so it is not reflexive. It is not partially ordered because it is not reflexive. It is not symmetric because if A is less than B, it does not imply B is less than A, but it is transitive. If A is less than B and B is less than C, A is indeed less than C. Any questions about this one? Number 5, greater than or equal to. This one is transitive. It is not symmetric because okay, I can give you an example. 5 is greater than or equal to 4. But 4 is not greater than or equal to 5, so it is not symmetric. It is anti-symmetric because in this case, if A is less than or equal to B and B is less than or equal to A, then A and B must be the same. So it is anti-symmetric. It is partially ordered because it is also reflexive, but it is also totally ordered because it is also comparable. Choose any 2 integers, and I can tell you which one is less than or equal to the other one. I only need one way, right? I don't need it both ways, but as long as I can find at least which one is less than or equal to the other one, I'm good. So this one is totally ordered. Number 6, if R is a relation defined over X is known to be reflexive, which one of the following do we know for sure, regardless of the actual definitions of R and X? So the only thing we know is there has to be at least as many elements in R as there are in X, because each element has to relate to itself. That's why the only thing we can really guarantee is this one. The rest, maybe, maybe not. Okay, it's hard to say. Number 7, if R is a relation defined over X and R is known to be symmetric, which one of the following do we know for sure, regardless of how R and X are defined? And the correct answer is we do not know. oh, I know what is going on because my browser is actually is taking up more screen space than there is actual screen space. So the other thing that I was trying to fix earlier is not because of my notes, it's actually because of I did not resize the browser right. There we go. So with this one, it is none of the other choices can be confirmed. So you gotta find examples and say, can I construct one where R, the cardinality of R is even? Yep, that's pretty easy because 0 is an even number. R can be empty. Can I make it not the same? Yes. And so on and so forth. So for every single one of these, I can find a way to do it. So as a result, the answer is none of the other choices can be confirmed. All right, is that it? All right, so submit quiz. And did I get? Yep, I only got 6 out of 7. I missed 1. Okay, which one did I miss? So,
I remember you putting.
if R is a relation defined over X is known to be reflexive to which of the following to be known?
I think you explained it correctly, you might have just clicked the wrong one.
You clicked the wrong one.
I did.
It did say greater than or equal to though.
Okay. That's very typical of me. As I said, I would make a great spy. They can capture me, ask me, and I can honestly try to tell them the right answer, and then just the wrong thing come out of it. Really bad for a teacher, but great for being a spy. All right.
So could it go up there, please? Could it go split up?
Up, some more. Number 2.
Why is this one number that way?
Why is it not totally ordered? Because, okay, so we are talking about integers, right? So let me pick 1 and 6. Are they related?
Yeah, no.
But the question says only want to look at equal to as a relation. So 1 and 6 are not related at all. And that's the reason why it is not comparable. And if it's not comparable, it cannot be totally ordered. All right. Any other questions about the relations topic?
Could you go over number 1 for transitive?
Yep. Okay, so number 1 is not equal to. It is not transitive because if I choose, that's a pretty easy one. If I choose E to be 1, F to be 2, and then G to be 1 again, then 1 does not equal to 2, we're good. 2 does not equal to 1, we're good. 1 does not equal to 1, that's a good.
Okay, so I was just checking because I wanted to make sure that E and G could be the same thing despite, or like the same number despite being different.
Yeah, that we can use 2 in this case as a bridge, but it's bridging from 1 back to 1, but 1 does not equal to 1 is false.
Right.
Yep. All right, any other questions about relations? Because relations is going to be in the second exam, in exam 2, so it is really kind of helpful to make sure that we understand all the concepts.
Yeah, total ordering. If I understand correctly. The third part where it's comparable, it has to be. It has to be in an order. Like a ranking system.
Well, the question is, how is comparable defined? Well, that's not how it's defined. So the key is, make sure that we know where to find the definitions. Okay, the definitions are very, very important. Sometimes the description of a definition may not actually tell us what it is, like anti-symmetry. It's like, what does it mean when you say something is anti-symmetric? Does it mean it's not symmetric? No. Anti-symmetric does not mean it is not symmetric. It has a different meaning. So when we talk about comparable, it is just as important to go by the definitions. Okay, the quantified expression is the key to get all of these things right. There's no avoiding your reading and trying to understand those notations. Yep.
Why is question number 1 not transitive? Because if 1 is not equal to 2, and 2 is not equal to 3, then 1 is not equal to 3. So it is transitive.
but it is a universally quantified statement, which means regardless of how we choose the values of E, F, G, we still have to make sure that ERF and FRG implies ERG. So, so earlier, when you chose E to be 1, F to be 2, G to be 1 again, then you can make 1 does not equal to 2 true, not a problem. 2 does not equal to 1 true, not a problem. So the conjunction is true. So we have the entire left-hand side of the implication being true. But then we have E and G being the same, right? They're both 1s. So now we can ask 1 does not equal to 1, which is the right-hand side of the implication, that is false. True implies false is false. So that means if I can find at least one case, okay, one way to choose the values for E, F, G, such that the statement being quantified is false, then the universally quantified statement is false. This we can find a counter example. All right. This reminds me of Indiana Jones movies. You know, when you guys will select your ringtone, choose wisely. I was about to rewatch Indiana Jones. Which one was that? The Holy Grail? The Last Crusade. That's right. Yeah, with Sean Connery. Yep. With the late Sean Connery. All right, any other questions? All right, so we're going to move back to the propositional logic steps. So where we were was right about here. Okay, so I gave you guys an example, and so what I want to do is to kind of go over this part here that was added about the same time last year, because I thought it would be helpful to illustrate the kind of problem that we're having. So we define a set W, and I'm using the set notation of W is a set where each thing beta is a WFF, and that's all. Okay, in other words, W as a set is a set of all the well-formed formulae. Okay, and we know how to construct well-formed formulae also, you know, because it's a we call it recursive algorithm again. We start with everything in alpha, okay, the set alpha. Each thing in alpha is by itself well-formed. So those are the ground cases of the recursive definition. And then you look at the operators in omega. So if you have a unary operator and is operating on something that is well-formed, the result is well-formed. If you have a binary operator and it has two things to operate on, and each thing is operating on is well-formed, then the binary operator, the expression using the binary operator is also going to be well-formed. So we can create an infinite number of well-formed formulae in most cases, even though most of them are probably useless or meaningless, or they have their duplications of others. So the W set is actually infinitely large, containing a lot of stupid, well-formed formulae, but nonetheless, they're well-formed. So iota is a subset of W, because everything in iota are basically well-formed formulae that are known to be true. They're given to you to be true. Don't ask why, but they're just given to be true. So we talked about that last week. So then we define D, which is also a subset of W, so that D is a set of WFFs, well-formed formulae, that are derivable from the elements in iota. So this means iota itself has to be a subset of D, because those are given to you to be true to begin with. So it has to form a subset. In this case, most of the time it is a proper subset, and it's not guaranteed. So I'm just going to say it is a subset of D. So now, assuming that theta, phi, and psi are elements of alpha, which means we are allowed to use these schemata. You remember, they're not called variables, they're called schemata because they are used in pattern matching only. They don't have meanings other than pattern matching. Each element E of Z or zeta is basically a rule for transforming. It has the format of M inverse WFFQ, theta, phi, and psi. Okay, so now we have to look into this notation here and go like, okay, what is M? M itself is a set of well-formed formulae that refer to theta, phi, and psi. In other words, we are using these Greek symbols to specify a pattern that we are looking for. Is that okay so far? I can give you some actual examples in just a little bit, but for now, I'm just explaining the theory of this whole thing. For example, an element of Z may look like this. So in this case, we're looking for two well-formed formulae, and they both have to be implications. The limitation is the first one, the right-hand side of the first one has to be the same as the left-hand side of the second. That's basically the only restriction on top of we are looking for two implication well-formed formulae that are somehow known to be true at some point in the derivation. Okay, so if you can find this particular pattern, two well-formed formulae, they're both implications, and then the right-hand side of the first one matches the left-hand side of the second one, then we use this symbol here to basically say, you know, we can now mark this particular well-formed formula to also to be true. So the new well-formed formula that we can mark to be true is taking the left-hand side of the first implication and the right-hand side from the second well-formed formula to make this new well-formed formula, and we can now mark this one to be true as well. So are we doing okay so far in this case? You know, just understanding the concept. I can give you an example with exactly this, you know, in just a little bit. So if you're not quite getting this, we can kind of go over the example later on. And this is a link. This is a hyperlink to a document that contains, you know, everything that most people use. So, and using kind of the same symbols too. So they use the inference symbol, and it is a long list. Okay, so each one has a Greek name as well. And I'm not very good with names, whether it's people or techniques in proof and stuff like that. But it's a long list. Okay, so I'll keep this one around for just a little bit. Now that we have the vocabulary to describe membership of D, first of all, by definition, iota is a subset of D. We talked about that already. And the inference rule goes like this. If A, B, and if there exists A, B, C in W, each one is well-formed, but not necessarily derivable. And there exists T in zeta, which means we have a transformation in zeta, such that T is in the form of M inverse WFFQ of the three Greek symbols. You know, we got theta, we got phi, and then we got psi to define where M and WFFQ come from. And WFFQ is okay, let me see what that means. If I think I might have a definition up here somewhere. Okay. All right, so for all WFF theta, psi, and phi and psi in M, M is a set, okay? So we are basically saying, you know, if I can make a match, WFF ABC is in D. So A, B, and C and the Greek letters are basically substitutions. A, B, and C are specific well-formed formulae in W. They may or may not be derivable. Theta, phi, and psi are wild cards. So we are basically looking for a match. Can we match A, B, and C as, you know, as specific well-formed formulae to the pattern that is specified by WFFQ of theta, phi, and psi? If that is the case, if we can make that match, then WFF A, B, and C, A, B, C would be elements in, would be an element, a single element of D. Is that okay or not? Is that making it worse? Okay, maybe when we go through the example in the next 10 minutes or so, it will help clarify what this means. All right, so what I'll do is I'm going to go through an example. There's one here already, but I want to go through another one kind of live. So this way, as I work on the example, you can ask questions. All right, so this is the example. Let me get rid of all the unnecessary stuff. So this time I have alpha having PQRST, phi, rho, theta, and psi. Okay, it's just a whole bunch of Greek letters. Omega this time has conjunction, disjunction, implication, if and only if, as well as negation. Iota this time does not have a single variable. So we have P implies Q, Q implies R, P and S. Okay, so those are the only expressions that are known to be true. Now, they don't say anything directly, at least not directly, about whether P itself is true or not. It doesn't say anything about Q is true or not. Okay, it is only the expressions that are known to be true. Are we doing okay so far with this? It's kind of strange iota. Yes.
Well, if P and S is true, can we not infer that P?
Yes.
Is okay.
Yep. So we're going to use that rule later on. So these are the expressions that are known to be true, and each one, P, Q, R, and P, each one is called a variable, which means each one can be true or false. Okay. So we don't really know individually, or at least not from iota, which one is true and which one is false. Okay, maybe we don't even care in the end which one is true, which one is false. It depends on what we want to prove from this specific iota. Okay. So zeta in this case has a bunch of stuff in it. So we got one rule, which is if I can find two well-formed formulae, okay, I shouldn't say that. If I can find well-formed formulae for phi and also for psi that are known to be true at some point, then I can infer that a conjunction of these two well-formed formulae is also going to be true. So are there actually any restrictions in this one? No. All I need is to say, is there a well-formed formula known to be true, and we'll call it phi, and then we'll find another one and call it psi. Yep.
Is that reversible? So if I find a
It is indeed reversible, but if you want to reverse it, you cannot use the same rule. So the transformation rules are only going in one direction. So if the logic behind the transformation is supposed to be reversible, then you need to write another rule to specify the reverse direction, which is also here.
Is that transformation rule necessary? Like if I didn't have that or the reverse, would I be able to say that P and S are true because P and S is true?
Okay, yeah, the first one is not required.
Okay,
Not in the derivation that I want to show you.
right, because the information is like implicit within the operator.
And the second rule is started with an anti-set, which means I don't even care about the pattern matching part. You can choose any well-formed formula in this case, even one that is not known to be true. I don't care, because the result is whatever you choose, we'll call that phi. So phi is just a well-formed formula. It doesn't even have to be known to be true. Phi or not phi is guaranteed to be true. Okay, it kind of makes sense, right? Because each expression is a Boolean expression, which means it can only be true or false. So if I take an expression that is Boolean and I OR that with the negation of the same expression, the disjunction has to be true because one of two sides has to be true in that case, right? Okay. The third one is particularly useful because the third one here is when we saw this one earlier, just using different Greek letters. So in this case, we need two implications, and the restriction here is the right-hand side of one has to be the same as the left-hand side of the other. So if I can find two expressions like this, then I can infer the left-hand side of one is going to imply the right-hand side of the other. And then we have the last one, second to the last one, where we have phi implies psi and also phi itself. In other words, I have one implication that is known to be true. I have one other well-formed formula that is also known to be true. And the well-formed formula that is known to be true also has to be exactly the left-hand side of the implication. So if I can find these two well-formed formulae, then I can infer that psi or whatever pattern is the right-hand side of the implication also has to be true. And then the last one is what you said earlier. If I can find, phi and psi, then I can also infer that one of them has to be true. Now, which one, I'm not really taking commutative into consideration here. It's kind of implied, we understand that this is commutative. All right, well, my watch just buzzed me, which means it's time to take roll. So we'll go ahead and do just that. And let me get to the thing quickly this time. And this is under propositional logic. And let me make it visible to you guys so you can now see it. There's also a QR code for your convenience. Second, can I? Okay, I guess I can preview it. This way the bitmap is going to show. All right. The word that I have chosen, I cannot remember. It's iota, that's it. So it's lowercase iota. Now, why does the phrase go like, I don't care about an iota?
Is it small or something?
Iota is small. Iota is small? Is it?
Yeah, I've heard it used in that way. Yeah.
Okay.
An iota of something is like a tiny, tiny amount of it.
Is it one of those symbols, where micro is mu, and does it have to do with the engineering units?
Maybe.
Now I'm a little curious, which is dangerous. All right, so are we good with the roll taking activity? Okay. You guys will be okay with the roll taking thing? Okay, all right. Yep.
The other day for those taking, I wasn't here when you said, did you press your voice there?
Say one more?
Are you recording today?
Yes, I believe so. Because I moved the Zoom window to the other part of the screen, but it is recording. All right, so let's go back to our Joplin example. There we go. All right, so the question now is, what is in W? Okay, so we'll work with W first. So W has a lot of elements. Many of those are kind of like, I'm not sure why it is here, but it is. Okay, so we'll take a look at a few elements that are in W, which is the set of well-formed formulas. So I can say P is in W, right? Because your P is obviously well-formed. Why? Because it is in alpha. Okay, and then we can make fancy stuff. Okay, so we'll make fancy stuff like P and P. It is also in W, right? Because the conjunction is a binary operator, and we already know that P is well-formed. So when you have two sides of the operator being well-formed, then the overall expression, which is P and P in this case, is also well-formed. So I can now just go with this and go like, what if I have P and that thing that we just ended up with earlier? Well, that is going to be well-formed too, because P is well-formed. P and P is well-formed. So this conjunction here, which takes on two well-formed formulae on both sides, then it is definitely also well-formed. So are we doing okay so far with here? What is in W? A lot of nonsense like this, okay? Along with other things. Are we good? All right. Yes.
Would P or P be considered part of W?
Say the one more time.
Would P or B also be considered part of
Yep.
W? Okay.
Yeah, I can tell you what it's not, okay, so if you have, just, and P, this would not be in W. That would not be right, because the conjunction is a binary operator, you cannot just give it one value. So this would not be in P. So I have to kind of say this is false, okay? There we go.
So as long as it's like the variable is alpha and the function is in omega, it should be part of W or?
Oh, it can be a lot more complex than that. It give you something that's totally a lot more complex. So I can now say P and Q, the whole thing implies S or T. That's also in W because you just have to break it up, right? So the last operator is the implication. So you have is the left hand side of the form, is the right hand side of the form. Okay, the left hand side is a conjunction. And you ask again, is the left hand side and the right hand side of the form. In this case, they're both from alpha. So we can now answer the question of yes, P is well formed, Q is well formed, P and Q is well formed. So the entire left hand side is well formed. Then we go to the other side, and then we have this S or T well formed. Well, we look at or, and then we ask, is it a binary operator? Yes. On both sides of the binary operator well formed. S is from alpha, it is well formed from alpha, so that's why it has to be well formed. T is the same thing. So now we can see that S or T is well formed. So at this point, we know P and Q is well formed, S or T is well formed. So the implication is also well formed because both sides of the implication are well formed. So we can make really complex, expressions, just by, kind of recursively analyzing whether, the operator has the right number of operands and whether each operand itself is well formed. Yep.
W just is a set that contains a bunch of well formed based on. Oh, okay.
Yep, using the definition of W that is coming from here, so it's just a set of all the well-formed formulae.
Is it exhaustive set of all of it or?
You tell me, what if you look at the definition where the mouse pointer is it exhaustive or does it just say, give me some of them and will be good? It is exhaustive. Every well-formed formula is in W and everything in W is well-formed. Okay, I think you are first and then you're second. Go ahead.
Going back to the S or T,
Uh-huh.
We don't know anything about T because it's just a symbol, but we know that
It's
S.
a variable, yes.
Okay,
Yeah, but I can confirm that this whole thing is in W because it is well-formed. Yep, go ahead.
One thing is, I would also be in W work.
Yes. That is by the very nature, by the very definition of well-formed formula.
Okay, so if I put a false on the left-hand side of the implication, then that makes the implication always true. So if I put, for instance, like, okay, all right.
I know what you're talking about. Okay.
Right, but I
let me
can't
see.
use that because, unless I only use that symbol for that, right? Because I don't necessarily know that in all other cases where I use the symbols on the left, they will also evaluate to not well-formed formula. Because I don't know that it's actually false. I just know that it's not
I don't
necessarily
care
true.
whether it's true or false. I just know whether it is syntactically correct. So I think this is what you're talking about. P and not P is guaranteed to be false because at least one side has to be false. So the conjunction has to be, oh, okay, I need to reverse it because we want a case where the implication itself is guaranteed false. So we'll go ahead and say this is the or, and then this is the and. Okay, that's better. Okay, so in this case, the left-hand side is well-formed, but it's guaranteed true. Doesn't matter whether the variable P is true or false, because, hey, one of these two has to be true, and we only need one side to be true for the disjunction to be true. When you look at the right-hand side, we don't know whether S itself is true or not, But we know that one of these two sides has to be false, and we only need one side to be false for the conjunction to be false. So in this case, we have true implies false, guaranteed, which means the implication is guaranteed to be false. But the question is not whether it can be marked as true or not. The question is it well formed? And the answer is yes, it is well formed.
Because it makes sense.
Because syntactically, it is in the correct order. It's just like in English and any other natural language, you can make sentences that are meaningless. But if you ask a person who knows grammar and ask, is it grammatically correct? They can say, yes, it is grammatically correct, but it doesn't have any meaning.
So that's why it's referred to as well formed.
Yes. Are we good so far? Say again?
How would you make it not well?
Like this one?
The very
Where
last.
the binary operator has only one operand, it is not well formed.
What
So that's why it's,
about the very last one? Like, can you get the P-
this one here?
Yeah.
You can take out one of the two sides of the implication, then it's not going to be well formed.
Can you use all of the, can you use the correct syntax, but make it still not well formed? Because like if you just used, for instance, T, right? If you were like T and T implies T and T, right? Since we don't know if T is well formed, then that is that.
Well, T is well formed, that's for sure, because it's coming from alpha.
I thought alpha isn't inherently well formed. It's just.
Everything from alpha is well formed.
Could you, if you have to use all the values, get a value in alpha, you just like take a random value, like a D, and have that D implies something.
Okay, so I will refer back to the definition in the reading material. See, this is, I know this is very annoying to some people, but this is my job to be annoying. Yes, it is. See this part here? See what it's saying? For all element E in alpha is a welcome, is a WFFE is true. So this tells us if you take anything from alpha and then you just take that thing and ask, is it well formed? The answer is yes, it is well formed. But you cannot take anything other than the alpha and ask, is this well formed? Because this is the ground case for qualifying what is well formed. The other definition is basically structurally create well-formed formulae using the operators.
We cannot use symbols that are not in alpha, correct?
That is correct.
Okay, so then all of the symbols that we are allowed to use are well.
Yes.
Okay. All right.
Well, everything in alpha is well-formed.
We can
And
only
they-
use the symbols
That is
now. So
correct.
then anything that we are allowed to use is well formed.
Yes.
Okay.
By itself, by themselves.
Yes.
But once you add operators, then you also have to play by the rule of if it's a binary operator, we need two well-formed formulae as the operands. Yes,
So what is the purpose of that? Is to find W?
to define W, just so that we know that we have a set of, this is the universe of everything, in the system. Yep.
No, like what's the purpose of the example?
The purpose of the example, well, we are not quite there yet. I'm
Oh,
trying to
okay.
get there. I'm still paddling the boat. But it's paddling as if I only got one oar in the boat. Yeah. All right, so are we good so far with all the examples? But I do have to emphasize, as much as I'm sounding like a dad, which I am, not to you, that it is important to read the material and actually get to the definitions, okay? It's important to get to definitions. So, getting back here, okay, so we kind of know what is in W, okay? So then the question is, what about D? What is in D? Okay, remember D is a set of well-formed formulae that can somehow be derived from iota. Are we good so far? Okay, so now we want to look into what is in D in this case. So the obvious stuff that is in D would be everything that is in iota to begin with, because they take they basically do not take any derivation to be there.
Isn't that just zeta? Why do you need D for that?
D is a set of well-formed formulae. Zeta is a set of transformations. So they are sets of different things. So in this case, P implies Q is an element of D. Why? Because it is in iota to begin with. Does that make sense? Okay, and as a result, I can also say Q implies what R is also in D, okay? Because that's also in iota, so you can see it in iota, we have Q implies R. So I can make the third one, which is P.
If we're laying this out, do we have to cite the rules that we're using? Like, because of rule something something in Zeta?
Well, the best thing about the way I teach this class is by the time we get to that part where you have to do some derivation, we can forget about all of this stuff that we are learning right now. Because I got a better way to do things. All right, but this is how people do things. So we'll go through how people do things first, and then we'll talk about how we can do it without this kind of cumbersome way of doing things. Okay, so this reminds me of a ChatGPT. This is how my brain works. It just fires randomly and then make connections. You can also think that I have a very small set of iota in my head, but there's a huge set of zeta. So it just goes like that. Anyway, ChatGPT. ChatGPT is interesting in the sense that it cannot add anything new because it was trained on text that people wrote 2 years ago. So what it is really good at is abstraction. It can extract the structure of sentences and it can say, hey, it's kind of doing what this is doing, okay? It just recognizes the rules by itself. The transformation rules were not given to ChatGPT. It figured it out. It was able to go through all the text, all the structures in terms of grammar and the content, and what sentence usually follows which other sentence, and which part of the first sentence appears as which part of the second sentence. It can track all of that stuff in a probabilistic way. And as a result, so it can take your prompt and then it can match it to one of the rules that it has already recognized and go like, oh, with a prompt like this, typically we start with this, and then we start with that, and then we go this here and here and here and here and here, okay? Which is not to say ChatGPT is a simple, simplistic program, but what I'm trying to make a point is it cannot add anything new. It is just a very good mimic of what we feed to the system. As such, it is not, in my books, it is not artificial intelligence. Because one, it is not artificial. Everything that it can spew out is trained based on what we have written as humans up to 2 years ago. Yep.
So would it then need some method of data input to it? So like it can update its data set by like reading books and whatnot, or going out into the world and getting visual data? Would that then
Count as
artificial intelligence? Because then it's,
but it's still not generated.
okay, we're not generating, right? Because what we do is we also just look out in the world for the alphas and the iotas, and
we challenge things that we believe are true. I'll give you an example in just a little bit, but let me finish what I was talking about, which I cannot remember anymore.
it's not artificial intelligence.
Oh, it is not artificial, and it is also not intelligent, because if you train ChatGPT with stupid stuff, stupid material, it will also just spew out stupid material. In other words, if the only type of content you train ChatGPT with are romance fiction, and then you ask it about a logical problem, it goes like, I don't think that's very sexy. I would totally not date propositional logic. Right? Because it has never been exposed to logical reasoning. The reason why ChatGPT can solve problems is because it has read about how people solve logical problems. That is how it learns. So there's nothing artificial and nothing intelligent about ChatGPT from that perspective.
are then humans not intelligent? Because if you think, I feel like if we train humans on trash data, we can get trash answers, right? So like, I was thinking about this when I was learning Chinese. It was like, well, what if the teacher's just lying to me and everything she says is just some made up gibberish language?
And you
she
just
came
learned
up
that.
with, Right? Yeah, and all of the rules are inconsistent. I just believe her.
Okay, so there are a few things that are interesting about what you just said, because language, including mathematics, is entirely man-made. Okay, okay, I should be gender neutral, people-made. Okay, so that means, all of that stuff can be gibberish. The question is, it is also a modeling system. So the question is, and when you apply those patterns, does it match reality? Is it a good model? So when you start to talk, in the gibberish, Chinese, quote unquote Chinese to an actual Chinese person, that person go like, I have no idea what you're talking about, right? So that means the model does not match reality, which means the model, as sophisticated as it might be, is useless. It has no application in the real world because it is not modeling reality. Are we good so far?
Yes.
All right. So let me get back to the other one, which is, so what do you mean by generating new content, right? Oh, before I do that, I also have to say at some point, ChatGPT will have to, excuse my language, eat its own shit. Because somebody is going to use your ChatGPT to create novels, and then that novel is going to be on the internet, and then ChatGPT will in return consume that ChatGPT generated novel back into its own training data. Okay, so at that point we have also known as inbreeding, which means the engine will only get dumber and dumber.
Well, not necessarily, because like they're doing this right now with Stable Diffusion. So like one example is I saw this video where they took and they used Stable Diffusion to they took like an anime and they used it for the art style, but it wasn't exact because none of the characters in the anime had beards, and the dude who was trying to get his picture in the art style had a beard, and so it didn't have any of that data. So then it generated a bunch, and then he selected all of the ones that had
is the
beards.
external factor.
Okay.
That is the external factor because somebody is evaluating and giving feedback to the system. So, but if everyone is just consuming and just go like, oh, I just want what you generated without any feedback, then the system will only degenerate over time. Yep.
So the only form of artificial intelligence to you is like unguided machine learning?
It would be not even machine learning. When I was in AI, it would be algorithmic type of quote unquote intelligent behavior because we wrote the program to make the machine do a specific thing. So playing chess, for instance, is to me, actual AI, even though by today's standard, it is kind of like, oh yeah, it's history because it's already done. The problem is completely solved. Finding the shortest path between 2 points in the graph, which we'll actually talk about in this class, was artificial intelligence in the 50s. I mean, if you think about in the 50s, okay, how many transistors in the processor? It'll be in hundreds of thousands at the most, okay, which is, you guys can say, yeah, I think my Fitbit can run circles around the mainframe computer. You would have been right, okay? But that's also why it is a shifting standard. What is considered artificial intelligence is always a shifting standard. It is always what we want machine to be able to do, but not quite there yet. Yep.
So what is your definition for artificial again?
It is generated by the computer. It's discovery by the computer. It can be the discovery of the shortest path. Okay, but the machine came up with that solution, using the algorithm. It is not regurgitating, all of the paths that we have pre-programmed into the system. So like, oh, I'm just gonna choose which one, using a sorting algorithm. Yeah.
So it has to invent new things.
I think in the end, I know this is like really, we're digressing further and further away from this class, but I think this is still a useful conversation. So I think eventually it has to connect to reality. In other words, you hook up the AI to the James Webb telescope, and then you let the AI to generate theories, but it has to be able to test the theory against, experiments that we can actually perform today. If something works out, it's good. You will basically say, this is a theory. but it is consistent with every experiment that we can derive. You can derive theories that do not work out, okay? So we can just kind of cross those out and go like, okay, they do not work out. Okay, one example is Einstein, okay? Albert Einstein came up with the one simple thing of saying the speed of light is constant. Seems pretty simple, right? But it is counterintuitive because if you're on a train that is moving and you're throwing in an object and not counting air resistance, the actual speed of the object would be the speed of the train plus the relative velocity of how fast you're throwing that object. But that does not work for light. Okay, if you shine a flashlight at the front of a train that's going half the speed of light, those photons going out of the flashlight is also going just at the speed of light, not 1.5 the speed of light. So coming up with a challenge like that is what makes us humans. Because that's quote unquote original. You're challenging something and go like, but what if we make that change? Would it still make sense? Now, Albert Einstein, it was a theoretical physicist. So he works out the math and go like, yes, it can make sense. It was until later that they can actually use telescopes to observe the curving of light around a heavy object in the universe. I think it was the sun. And they were able to go like, yeah, we're not supposed to be able to see that star. It's supposed to be behind the sun, but we can see it because the light bent around the gravity field of the sun. So there was confirmation about, the relationship between, the speed of light, gravity, time, as well as space. Entanglement, okay, quantum entanglement was actually, I know we are going really far away from CISP440, but I think this is really important because I think it is important for us to understand what makes people and the limits of something like ChatGPT, because you guys will be competing against, ChatGPT, okay? Why do you think they should pay you to do something, right? So quantum entanglement, that's it. So Albert Einstein came up with relativity, and Bohr took that theory and worked out the math and predicted that in quantum mechanics we can have entanglement, where one thing you observe the state of one thing, and then the matching thing on the other side would automatically change the state to this thing here. They're supposed to be opposite. So Bohr basically approached Einstein, go like, well, according to your math, this is supposed to happen. Actually, I take it back. Bohr worked out quantum mechanics, and then Albert Einstein said, no, this cannot be true. So in the process of Einstein trying to prove Bohr wrong, he came up accidentally with the theory of quantum entanglement. And nobody knew the answer to that question. Is it real or not? Okay, who was right and who's wrong? Nobody knew, except in theory, if what Einstein said was right, then quantum entanglement should happen. But nobody was able to prove it until a few years earlier. And nobody knew whether the entanglement effect has to play by the speed of light rule. Okay, because we didn't know. We did not have experiments to do it. We did not have the technology to conduct those experiments. So being able to find out what experiments are needed in order to validate or to prove a theorem wrong is really important. And then you conduct the actual experiments, observe the results of the experiment. Then you can confirm whether a theory is at least consistent with every experiment that we can derive at a certain point of time, because with better technology, we can derive more experiments. Yes.
Okay, so I remember, I think it was last class, you talked about, you'd give us like A, omega, iota, and zeta, and then you'd give us like some W or something, and then we would have to say, like, is this a well-formed formulae? And then we'd have to figure it out by writing out a bunch of the W's and making it logically make sense. So then that would be like what you need. That's like us designing the experiment, right? Because you can take the W's in any direction because there's a million different W's. And so if ChatGPT was able to do the same thing where it was like, okay, I need to get to this information and prove it either true or false. And I have like these basic set of rules and information that I know, and then it extrapolated in a logical direction to get to it, like every time, then that would be artificial intelligence, or at least intelligence.
Yes.
Okay.
But it does not actually, ChatGPT does not inherently understand logic.
Right.
Because I tested it, and the answer, when you ask it the logical problems, the answer is sometimes right, most of the time is right, but occasionally it will get it wrong, because the generative process or the transformer technology of ChatGPT is probabilistic. It is not deterministic.
Right.
And logic is not probabilistic. I mean, you can use logic to argue about things that are probabilistic, but logic itself is not probabilistic. So, so I'm not really sure how much you guys are taking out of this discussion. Yes.
Is that a limit of being used to train it? Like if we trained ChatGPT on an internet made of just discrete math, right? Then could it learn logic?
It will be able to extract a pattern. Yes. So that's a very good question. I think it really does have to do with the ambiguity that is inherent to English, but more so, it also has to do with the probabilistic nature of the neural network. Because the neural network is trained based on, okay, I think this comes after that. Okay, that's just what the neural net is originally randomly configured to do. So you give it feedback and say, no, that's wrong. So the neural network would use the back propagation mechanism to try to converge to a solution where it would get most things right. But a lot of that depends on what is the original configuration of the neural net. The initial state of the neural net has something to do with what it can learn, what it cannot learn, what it can get right, and what it cannot get right. And then your training sample is the other one. Okay, even the ordering of the training sample can also impact what it can learn and what it cannot learn, and what it can learn right and what it can learn wrong. The logic does not allow that, right? Independent of the ordering of the presentation of the material, you should still not learn something that is wrong. So
that's why the chess AI would be artificial intelligence, is because instead of just saying like these are the probabilities and so this is what I'm going to, if as soon as it locks down a checkmate and it knows that it has like mate in 47, right? Then it's like these are the steps based on the rules, because it put out all of its feelers and it says, I know the path.
Yep.
Okay.
And just a quick question.
Yep.
What's the difference between probabilistic and deterministic?
that is a very good question. So probabilistic means, given a certain state, okay, you are trying to accomplish a certain thing. The question is, if you take a specific action, does it always lead to a particular state? So if it is deterministic, then every single time, if you start with this particular state and you take this particular action, you always result in that particular state. That is deterministic. In probabilistic type of scenario, you're given you start with the same state, you take a specific action, there's a 60% chance you end up here, another 20% over here, another 10% over here, and then another 10% over here. That will make it a probabilistic type of approach. And ChatGPT is definitely probabilistic because you can give it exactly the same prompt and will generate slightly different outcome from those same prompts. Yes.
Is the difference between artificial intelligence and what ChatGPT is probabilistic thinking or approach and deterministic approach?
So ask the question one more time.
Like the difference between the chess AI
Mhm.
and ChatGPT. So
Mhm.
chess AI, you
Yes.
consider real AI.
So it depends also, because, if your chess AI can actually figure out everything up to the end game of all the branches, then the chess playing computer or AI is completely deterministic. Now, on the other hand, if you don't have enough computation power and you can only work up to a certain number of steps and you can only evaluate using some kind of heuristic of how good is that position or that board configuration, then it can still be probabilistic because this one looks good, this one looks kind of good too. So maybe I would take either approach down here because they both lead to a fairly good situation, but it's not 100%.
So it's only like AI when it figures out the end, says like it has mate and whatever.
Right, but the modeling is 100%. Because in every single step in the chess AI to try to figure out what is the result of making a particular move, the resulting thing in its own simulation is 100% correct. That is not probabilistic.
So knowing the right result.
Yep. Yep.
I was just thinking, so you can't really extract the data from the probabilistic, like the rules exactly. And from the deterministic, you have the rules like from the chess.
Right.
Whichever moves are good.
Yep. And then there are games like backgammon, where the game itself is partially probabilistic because you have to throw a dice, but it is still quote unquote AI because the AI understands how the distribution is supposed to distribute, as opposed to learning by observing, go like, well, from my observation, that has a 20% over here, this one has a 60% over here. No, it is assuming that your dice is fair and each side landing on being on top is exactly 1/6. So it is still using proper mathematics and logic when it's trying to predict what is the best thing to do at this point. So so that's going to be a very interesting topic in the near future, because we know that most people are flocking to the ChatGPT approach of doing things because it is very cool, okay? But at the same time, if you rely on that type of AI to make important decisions, that may not really be the best idea because it is not 100%. Because it also depends on how you train the AI.
Yep. So what you would call AI is like what AlphaZero did. So then AlphaZero was developed by Google. It created a couple of different games with itself, learned patterns, and then it was against Stockfish, and then it beat Stockfish like how many times it was something. So it beat the chess engine. But it wasn't trained based on the previous human games. It didn't itself.
But the feedback is still based on the rules of the game. So you still need some sort of feedback like that. I would say it's a hard feedback based on reality. If there's a hard feedback based on reality, then you have a better chance that the AI would actually learn something that is useful. Yep.
Yeah, so I watched a video where they pit ChatGPT against Stockfish, right? And it was interesting because ChatGPT kept making illegal moves because it doesn't understand or play by the rules of chess. So it would just be like, well, it would be good, like it increases my win probability if my rook appears next to their king. So even though it couldn't move a rook next to their king, it just made one appear. And so that's why ChatGPT is like, it just does things based on what it thinks will allow it to win, but it doesn't follow rules and specific pathways that it is calculated.
It has no specific rule. It doesn't have the concept of specific. All right, well, we're getting back to the boring stuff here, but this is all right. So what I'm doing here is I'm observing this last transformation. So I'm looking for a way to substantiate the Greek letters using things that I know is in the set D already. Okay, so one way to make this part match is to say, hey, if I make phi the same as P, the first question is P a well-formed formula? Yep, pretty good. And I make psi equal to S, is it well-formed? Now, is P in D itself? No. Is S in D right now? No, we don't know yet. Okay, we haven't gotten to that step yet. But that's not even a question because I just need phi and psi, which is now translating to P and S. Is that in D? Yes, because it is in iota to begin with. Is that okay? All right. So by using this substitution, okay, makes it possible to fire the rule, and I'm just going to copy the rule here, which is phi and psi as the left-hand side of the infer E dash, and then the right-hand side is just one of them. In this case, it is the phi. Okay, so am I doing okay so far? You know, looking at P as a well-formed formula and say, well, make the placeholder phi the same as P, make the placeholder psi the same as S. Now I can fire this rule because P and S is in D already. It is actually in iota itself. Are we good? So once we fire this rule, what do we do? Okay, once this rule fires, then we know the result, which is P, is also in D. Is that making any sense? This is one application of one of the transformation rule based on what we currently know is in D. Yes.
So we're updating D based on the rules of C.
We are not so much updating D, we are just trying to figure out what elements are in D. In other words, the membership of D is already done, but we don't know yet, what is in D. So we are really just trying to figure out what is in D. So we start with things that we put into iota and say, okay, these are for sure in D. But now by firing this particular rule, we also know that P by itself is also in D. Now P is not in iota, okay? The way I defined iota earlier, P itself is not in iota. But because of using a transformation rule and also what is already in iota, now I can say that P as a well-formed formula is also in D.
And D is finite as well, right? It's finite set.
No, D does not necessarily have to be finite because if P is in D, then so is P and P. So it's P and P, the whole thing and P. So it's that whole thing and P again, and so on. So D itself is most likely to be infinitely large as well. But we know that D is a subset of W because it doesn't make sense to talk about things that are not even well formed to begin with. Is that okay? So that's one firing of one rule. So we'll try to fire some other rules, okay? So now we can say, let's make phi, I'm looking at the chain of the implication. So I'm not going to make phi the same as P. And this time I'm just going to use one single line to do all the substitution. And then we are making psi the same as Q. Q is the bridge. And then we'll make rho the same as the other side, which is the R. Okay. Okay, so what we are looking at here is a proposed way of substituting things. Okay, so I'm proposing that the wild card, okay, the placeholder that we know as phi to be the same as the variable P, psi is the same as Q, and then rho is the same as R. They look kind of similar, but not the same. Okay, the P and the rho can be a little bit of an issue. So using this particular substitution, I can now fire the rule. Okay, so which rule am I going to fire? It is the chaining of implication that I'm going to fire, which basically starts with phi implies psi, and then psi implies rho. So if you can find me two well-formed formulae like that, then I can also mark something else to be in D, and that would be going from phi and make it imply rho directly. Does that make sense? So if I make this substitution here, then I can find P implies Q. It is in iota to begin with. right? Can I find Q implies R? The answer is yes, we can find Q implies R that is in iota as well. So anything that is in iota is automatically in D. So I can indeed find these two things in D. Is that okay? So what, yeah,
I'm just saying, isn't this the same thing that's in Z,
in Z?
or am I thinking? wrong?
No,
Yeah,
Z is the set of all the transformation rules.
Yeah, but specifically what theta, I'm really bad for the Greek names. That also exists inside Z.
Yes, you can only use the rules that are in Z in Zeta. But this makes me then okay, let me finish this and then we'll take a look at what we have come up with as a conclusion. Okay, so now we can say P implies right arrow R is also in D. Does that make sense? Okay, so this is a slightly more complicated rule because there's a restriction of A has to do the left-hand side of that thing. But are we doing okay so far in terms of the Greek letters are basically just placeholders. They're placeholders for well-formed formulae. Okay, it can be a single variable, can be huge. It doesn't matter. It's just a placeholder. Yep.
Can you do one example with the empty set?
With the empty set,
Transformation.
but it won't get us to the conclusion that I want to get to.
Okay, great.
We're only one step away, okay? So now the question is, can I confirm whether R is true or not? Okay, in other words, the theorem I want to prove is R being true. So the question is, can I get there? The answer is yes, I can now get there, okay? So let me finish this in the next 3 minutes. So this time I will make phi the same thing as P as a variable. I'm going to make psi the same thing as R as a variable. And then we can fire the rule. That would be the second to the last one, where we have phi implies psi. And then we have phi all by itself on the left-hand side of the inference. And then we do a B dash to the other side, which is S, the psi. Okay, so are we doing okay so far? In other words, is P by itself well-formed? Yes. Is R by itself well-formed? Yes. Then I'm asking if phi is P and psi is R, can I find the well-formed formula, which is P implies R to be in D at this point? Can we confirm P implies R is in D? Yes, we just did. Okay. Can I also confirm the left-hand side of the implication using the placeholder phi, but phi is instantiated to P? Can we also confirm that P itself is also in D at this point? Yeah. Yes, we did it 2 steps ago. So now I have 2 well-formed formulae using this particular substitution method such that both of these can be found on the left-hand side of the inference rule. Then we can fire that rule, right? So when we fire that rule, whatever specifies on the right-hand side of the inference is also going to be confirmed to be in the set D. Okay, so now we can now say, then we know that in this case, R is also in D. In other words, now we know R is true. And if that is the theorem that we want to prove, this concludes the theorem. Yep.
So you're saying like if you gave us a prompt, prove R is true, then that's how we would do it?
Yes.
Okay.
So given the iota, which is initially what you're told to be true, and I say, can you tell me whether R being true is a result of whatever is in iota is true, then these would be the steps to get to it. Okay. But I'm only giving you a very small subset of all the transformation rules because as the other tab in the browser suggests, there's a huge set of those rules. Yes.
So how is D defined?
D is, okay, so the way we define D in the notes is down here. So the D is the set of all the well-formed formulae that are derivable from the well-formed formulae in iota. That's how D is defined. Now, but which one is in D and which one is not in D, it's difficult to tell, like, it's difficult to spell out. So we can only discover the membership of who is in D step by step. You first and then you, go ahead. They're derivable from I. In other words, if we assume everything in I is true, then we can make the conclusion that everything in D also has to be true. Yep.
So when I was looking at the zetas, it feels like all of the transformation rules were like implicitly true based on the operators that were being used. Are there, like, can you give us transformation rules that aren't implicitly true based on?
Oh, easy. Yeah, you can make very stupid transformation rules.
To then prove what
It's the same thing as training ChatGPT with only romance, fiction, and you're trying to get it to write a science, paper.
Okay.
It would be the same thing. It's like
based on this.
gibberish comes out. It's like, yes. Well, it can come up with something funny like, yes, protons are indeed attracted to electrons, right? And they're just, they're dating each other. Okay, but then, the real science part will be entirely missing because the model does not match what the model is supposed to be modeling. So, right. Yeah, that's basically is what we call a soundness problem, whether it is correct or not.
Have to prove, like, were we proving that R was true in the?
Yes, this is the proof that R has to be true. If everything is in iota are true, then R has to be true.
Even though zeta can have false stuff in it?
Well, based on the statement that we have already talked about.
Yeah, so in a universe where all of the zeta makes sense, then this would work.
But if a zeta is false, we cannot really prove R is true.
So if zeta is wrong, then whatever conclusion you come up is useless because it does not actually reflect logic.
Okay, so we cannot really prove R
So,
is true.
so what is in zeta are completely syntactical transformations. It's just a bunch of regular expressions and say, extract this from this regular expression, extract that from the other regular expression, come up with this new thing based on those two components and make that, also a part of D. That's all it does. It doesn't understand the meaning of anything. It's just pattern matching. That's all it's doing. That's all it's doing.
So zeta is just like the rules of the game. And so we can
Yes.
define them however we want, and then inside of that game, whatever we determine to be true will be true.
Well, we certainly hope so.
Yeah.
Just trying to like understand, like, something in my head. No, I'm not gonna ask. I just want you know.
Okay, so we'll let Justin go first.
Just thinking, so I'm sucking out the Greek names. So alpha contains all of the possible variables and
Schemata.
schemata.
Uh-huh.
Omega contains all of the possible operators you can use. Iota is the rules.
No, iota is the set of all the well-formed formulae
All the
that are
okay.
given to be true.
Given-
Don't ask me why they're true. They're just, you're
Those are
just
given
told
to
that
be
they're
true.
true. Yeah,
And zeta is
on the transformations.
the transformations that are given to you.
They're basically how you can derive something syntactically.
Okay. And then here W is a set of all well-formed formulae that you can derive from I. And D is
D is the set of everything that is derivable.
everything is
From I.
derivable.
Yeah, so it's a huge set. It's probably infinitely large. So I'm not concerned about listing everything that is in D. There are only just a few things that I want to know. Is that in D? Because it would be kind of, it's totally pointless to try to enumerate everything that is in D.
So W is all the well-formed formulae from A. D is all the
From A and
A and I.
omega.
Omega. And D is all the derivatives from I. And then so.
But D is everything that is derivable from iota.
Yes.